Like, subscribe, and hype the video. Also, leave a comment on any topics you want to hear about in the future. Okay, let's dive in. In 2015, a group of citizen scientists combing through data from NASA's Kepler Space Telescope noticed something they had never seen before around any of the 150,000 stars Kepler had been monitoring. A star roughly 1,400 light-years away was dimming. Not slightly, not briefly, and not in any pattern that matched anything in the known catalog of natural astronomical events. It was dimming by up to 22% at irregular intervals, in shapes and patterns that didn't match any planet, any known type of debris cloud, any binary star companion, or any other natural explanation astronomers could immediately reach for. And when researchers dug deeper into historical photographic records of the same star, they found evidence suggesting it had been gradually fading overall for over a century. The star was officially designated KIK 8,962,852. Most people now call it Tabby Star, named after the lead researcher who brought it to scientific attention. And to this day, it remains one of the most genuinely debated, most carefully studied, and most poorly understood objects in the entire observable sky. Today, we're walking through everything we actually know about it, and in our next episode, we're getting into the theories, including the one that made headlines around the world. Stick around for that one. To understand how Tabby Star was discovered, you first need to understand what the Kepler Space Telescope was designed to do. Launched in 2009, Kepler was built to stare at a single patch of sky containing roughly 150,000 stars simultaneously, monitoring the brightness of each one continuously over a period of years. The goal was to detect transits, the slight, predictable dimming that occurs when a planet passes in front of its host star from Kepler's perspective, briefly blocking a small percentage of the star's light. A planet the size of Earth passing in front of a sun-like star causes a dimming of roughly 0.01%, tiny but detectable with Kepler's precision instruments. The mission produced an enormous flood of data that professional astronomers couldn't process entirely on their own. That's where a citizen science project called Planet Hunters came in. Volunteers from around the world were given access to Kepler's light curve data, graphs showing the brightness of individual stars over time, and asked to flag anything that looked unusual or interesting for professional follow-up. It was Planet Hunters volunteers who first flagged KIK 8,462,852 as something worth a closer look, noting that its light curve looked like nothing else in the dataset. When professional astronomer Tabitha Boyajian and her colleagues investigated the flagged data, what they found was genuinely strange. Like, subscribe, and hype the video, because what those light curves actually showed is unlike anything ever recorded around any other star. A normal planetary transit produces a very specific light curve signature, a clean, symmetrical dip that repeats at perfectly regular intervals matching the planet's orbital period, with a depth that stays consistent from one transit to the next. It's predictable, regular, and easy to identify once you know what you're looking for. Tabby Star's light curves looked nothing like that. The dips in brightness were irregular in timing, irregular in depth, irregular in shape, and in some cases stacked on top of each other in complex patterns that suggested multiple overlapping objects rather than a single clean transit. The largest dips recorded reached a depth of approximately 22%, meaning the star's light was being blocked by something covering roughly 22% of its visible disk. Compared to Jupiter, the largest planet in our solar system, which would only block about 1% of a sun-like star's light during a transit. Whatever was causing these dips was not a planet. It was something far larger, far more complex in shape, and far less predictable in behavior than any single planetary body could produce. And the shapes of the dips themselves, asymmetric, with gradual ingress and sharp egress or vice versa, and complex internal structure in some cases, suggested the blocking material was not a solid, uniform object, but something extended, irregular, and possibly changing over time. The dipping light curves were strange enough on their own, But when researchers dug into historical astronomical records, photographic plates from observatories going back over a century, they found evidence of something even harder to explain. Comparing old photographic records of the region of sky containing Tabby Star with modern measurements, researchers found evidence suggesting the star appeared to have faded overall by roughly 20% between the late 1800s and the present day. A subsequent analysis using data from the DASH project, which digitizes and measures archival astronomical photographic plates, found evidence consistent with significant long-term fading over approximately 100 years. This long-term dimming added a completely new dimension to the mystery. Short-term dipping could potentially be explained by a cloud of debris or dust passing in front of the star on orbital timescales. But a century of gradual, overall fading pointed towards something affecting the star on much longer timescales, something that wasn't just passing in front of it briefly, but potentially surrounding it more extensively, or changing its output more fundamentally. Like, subscribe, and hype the video, because researchers were now dealing with not one mystery but two layered on top of each other, and no single natural explanation was cleanly accounting for both. Almost immediately after the initial paper describing Tabby's star was published in 2015, the astronomical community began proposing natural explanations for what was being observed. This is exactly how science is supposed to work. An unusual observation generates multiple competing hypotheses, each of which makes specific predictions that can be tested against additional data. The leading natural explanations proposed included a massive swarm of comets or comet fragments in an unusually dense configuration, a large cloud or clouds of circumstellar dust orbiting the star at various distances, the aftermath of a collision between large planetary bodies that had generated an extended debris field, and an unusually large ringed body or system of rings causing complex transit signatures. Each of these explanations faced real challenges when tested against the actual data. A comet swarm large enough to cause 22% dimming would need to be extraordinarily massive and unusually numerous. Estimates of how many comets would be required pushed into implausibly large numbers. Dust cloud models struggled to account for both the short-term dipping patterns and the longer-term overall fading simultaneously without requiring very specific, somewhat contrived configurations. Collision debris models faced questions about the timing and what kind of collision could produce material distributed in the specific patterns observed. None of these explanations was ruled out definitively by the data available. But none of them provided a completely clean, fully satisfying fit either, which kept the mystery genuinely open and genuinely interesting. One of the most exciting developments in the ongoing study of Tabby's star has been the effort to catch dipping events in real time using coordinated ground-based observations, rather than relying solely on the historical Kepler data. Tabitha Boyajian and her colleagues ran a successful crowdfunding campaign to fund a dedicated observing program using the Las Cumbres Observatory Network, a global network of robotic telescopes that can coordinate observations from multiple sites simultaneously. This multi-telescope approach allowed researchers to observe Tabby's star in multiple wavelengths of light simultaneously during dipping events, which provided crucial new information. During dipping events observed in this real-time campaign, researchers found something significant. The dimming was not wavelength neutral. Blue light was being blocked slightly more than red light during the dips, a characteristic behavior of fine dust particles rather than a solid, opaque object. A solid object, whether a planet, a spacecraft, or any other uniformly opaque structure, would block all wavelengths equally, producing a flat, color-neutral dimming. The wavelength-dependent dimming pointed specifically toward fine, translucent dust as the primary blocking material. This was an important finding that pushed the explanation toward dust-based natural models rather than solid artificial structures. But it didn't fully resolve the question of why the dust was distributed in such unusual complex patterns, or what was producing and sustaining it. So here's where the real observational science stands on Tabby's star. Irregular dips of up to 22% in a pattern no natural explanation cleanly accounts for. a century of overall fading in archival records, and real-time observations that have narrowed the culprit toward fine dust, while leaving the question of what's producing and organizing that dust still genuinely open. In our next episode, we're getting into the theories, all of them, the dust cloud explanations and their remaining problems, the intrinsic stellar variability argument, and yes, the one that made Tabby Star famous around the world, the alien megastructure hypothesis. Proposed not by internet conspiracy theorists, but by a credentialed researcher in a published scientific paper. What it actually claims, the evidence for and against it, and where the scientific community stands on it today. Stick around for that one. Like, subscribe, and hype the video so you don't miss part 2, and let me know in the comments what you think is causing Tabby Star to behave the way it does. I'll see you in the next one.